So we're going to talk about VSEPR theory, which is valence shell electron pair repulsion. And like it says, it's got a lot of words, it's got a bunch of words in there, but the only thing that really matters in there is that we know that electrons and electron pairs are negatively charged. And if you have electrons that are near other electrons, at least electron pairs, they will try to repel each other. And so this is just a way of trying to understand how do molecules get specific shapes based on thinking about the electrons that are surrounding central atoms and how they're repelling each other. Okay, we're done. We can stop now. I've said that. I think that we should do a couple of molecules. How about that?
Yeah, definitely.
Okay. So I want to start off with hydrogen fluoride. And I want to think about the fluorine. And as we've seen earlier, hydrogen fluoride is hydrogen sharing a pair of electrons with fluorine, and the fluorine also having 6 other electrons to make up its octet, and those 8 electrons form 4 pairs. So far, so good?
Yeah.
Okay, so now the tricky thing for you and I is to think about if those electron pairs have some sort of, if they're all negative, they want to repel each other. They want to push themselves as far apart from each other as they can. And in order to understand what the geometric implications of that repulsion are, it's helpful to have some sort of physical device that you can use. And so I brought one. I brought a lump of carrot. And this carrot is going to represent the fluorine. And I'm going to put some electrons around my carrot. You got some toothpicks. Okay?
Yep.
But before we get to 8 electrons around the fluorine, we're just going to start putting some together. So what I'm going to do first is I'm just going to quickly take 2 sets of electrons and put them on my fluorine. So I'm going to take away 2 of them for the time being. And I'm going to take 1 pair of electrons and I'm going to stick them in my fluorine. Okay? Just like that. And my other pair of electrons are going to go somewhere else attached to this fluorine, but it's not exactly clear where. Okay? So if I stick my second pair of electrons right here, that looks unorthodox to us, but it also might point out that if these electrons are trying to get as far apart from each other as they possibly can, this distance on this side is a lot less than this distance all the way around on this side. Right?
Yeah.
So they're not as repelled as far apart from each other as they possibly can be. So to get further apart, this pair of electrons, I'm going to slide further and further and further and further and further around until, oh, now I've got it over on this side. This distance is now further than what we had before, but it's not the same as what's on this side. And so those electrons are not repelling each other as far as they could. In fact, actually, in order to get them to repel each other as much as they possibly can be, they're going to go across from each other. And so in this case, I've got two pairs of electrons, and the angle between the pair of electrons on the right and the pair of electrons on the left is 180 degrees. So far, so good?
So far, so good. They look as far as apart as they could be.
Yeah, they're as far apart as they can be. Now, that's easy for two pairs of electrons. What if I bring in a third pair? I'm going to take my third pair and stick it right there. Now I've got 90 degrees, 90 degrees, and 180 degrees. That didn't work. They're not. What about if I take it out of the bottom here and I stick it in the top? Now I've got, if I rotate just a little further, I basically got the same thing I had before. I've got 90 degrees, 120 degrees, and looks like I put it a little crooked. Not quite 90 degrees, but 90 degrees. So if I want to get these three pairs of electrons as far apart from each other as they possibly can be, I've got to do something different. So I'm going to go back down here, and depending on how your geometry skills are, you're going to start to think about where we might be able to move them to. You'll know that getting them as far apart from each other in 360 degrees all the way around means that this angle is 120, this angle is 120, and this angle is 120. So if I have three pairs of electrons and I'm trying to get them as far apart from each other, it's 120 degrees. How am I doing?
So far, so good. I think the geometry checks out.
Okay, two pairs, 180. Three pairs, 120. Okay. Let's bring in a fourth pair of electrons because we're headed towards fluorine with 4 pairs of electrons. So I'm going to stick this one right in the top. Looks pretty promising. I've got 90 degrees, 90 degrees, 90 degrees. Those are all the same. But over here, I have 120, 120, 120, and all the way over, I've got 180 up and over to this side. So I've got a lot of different angles going on there.
Yeah.
And so in order to make those equally spaced, I'm going to have to take my 90s and make them a little bigger. Now I've got, my angles are a little bit bigger than 190. Sorry, a little bit bigger than 90 and a little bit smaller than the 120 that I had before. And in fact, in this case, it's 109 degrees. Okay, ask a question, Kevin. Or make a comment.
All of them are 109 degrees, or are any of them different, like before?
Right, right. Well, if I've stuck them in there very well, they should all be the same. They should all be 109. I bet
Okay.
you've got an example of one that's a 109 and it's perfect, don't you? Because you're not using a caret.
I can show it if you want.
Yep, yep, let's bring it up. I'll bring up your video.
Oh,
Okay.
shoot.
Yep, there we go.
My hand is so big.
There we go, perfect. And that's perfect. And you can see that they're that it's not a 90-degree angle, that they're just set off from a little bit larger.
Yep.
Perfect.
You can pin your video again then.
Yep. So that says that when we have 4 sets of electrons, the arrangement of those electrons tries to go to 109 degrees. Okay, so far so good?
Yep.
So with valence shell electron pair repulsion theory, we've got pairs of electrons that are trying to get as far apart from each other. And in general, if we've got 4 sets of electrons, they'll be at the orbitals will be about 109 degrees from each other. And we've gone from flat molecules that could easily fit on our piece of paper to something that is definitely 3-dimensional.
Mm-hmm.
Okay, so let's put, now I've got my fluorine with its 8 electrons. Now let's put my hydrogen on. My hydrogen is sharing, here's a hydrogen sharing a pair of electrons, and I'm gonna make it this set of electrons, and here comes my hydrogen. Okay?
Looks good.
So if we do all of those things, we can say, hey, we can see where some of the electrons are on our molecule. You can see this one that's pointing up in the air directly at the camera. And then we could say, hey, take a look at this molecule. Now, we've got, if I flip it this way, we've got hydrogen and fluorine. And so the shape of the electrons around the fluorine, there's 4 of them, so we would call the electron shape. Around the fluorine, is tetrahedral. Tetra meaning 4, right? So the shape is, it's a 4-sided shape, tetrahedral. But the molecule looking down the axis between the hydrogen and the fluorine, the molecule is linear.
Yeah. I have another example if you want to check that out.
Sure.
Yeah, so all of these are the electrons, right? So
yep.
If you just look at the electrons, you can see it's tetrahedral, like Dr. Hunter said. But if I have another model, just the atoms, you can see that that shape is linear. But
yeah, nice.
The electrons are still there.
Right. Okay, that works. Let's do another one.
Okay.
We've seen when we do water, that the oxygen has 8 electrons around its central atom. And sometimes we've drawn it like this with the hydrogens on either side when we're doing a Lewis structure, or sometimes we've drawn it like this. Fair enough?
Yep.
Okay, so this time I'm going to make my central atom be my oxygen. And it just so happens I've got an oxygen right here. It's the same caret I had a second ago, right? It's useful that way. And so here is my oxygen with its 4 sets of electrons around it. 1, 2, 3, 4. And here are the 4 bonds. So we know right off the bat, the the electron bond arrangement is tetrahedral. Right off the bat. And I'm going to bring in two hydrogens. Well, there's one hydrogen. Here's a second hydrogen. And let's say that I orient this one up next to my molecule up there. I'm going to hide the one, use this, there we go. So I'm going to put a hydrogen on this side, and I'm going to put a hydrogen on that side, just like it's got in that top diagram. Fair enough?
Yep.
So let's stick them on there. So that's oriented the exact same way. I still have my tetrahedral arrangement of electrons around my central oxygen. I've got my hydrogens on either side. And so the electron bond arrangement is tetrahedral. And so then the question is, what's the shape of my molecule? And if I look around, there are a couple of different words that are used to describe this shape. Sometimes it's called V-shaped. And sometimes it's called bent. So we did that one by having the hydrogens across from each other, right?
Yep.
Well, the one below says, let's put a hydrogen here and a hydrogen at the bottom, right?
Yeah, sure.
Well, it seems like that could be different. Let's stick it on there. Stick it on there. So now they're oriented close to the way the diagram is underneath. Same oxygen atom. And as I rotate it around, oh, we're going the wrong way. There we go. There's my V shape. There's my bent shape. And so I do it in both ways. So you can see it doesn't matter which electrons, sorry, which electron pairs get the hydrogens, you still end up with this same shape.
Yeah, that's very true.
Right. And so one of the challenges in this course and other courses like this is to be able to look at this water molecule written flat on a two-dimensional piece of paper, or this water molecule written flat on a two-dimensional piece of paper, and be able to go back and forth and recognize that in both cases, we're really talking about the same molecule and that it's V-shaped. And that's because the pairs of electrons around the central atom are repelling each other as far as they possibly can. I want to do NH3, ammonia. So for ammonia, we've got nitrogen, group 5, 1, 2, 3, 4, 5. It needs 3 electrons. We've seen from our Lewis structures, 1, 2, 3. The nitrogen has all 8 of its electrons. It's nicely satisfied. The hydrogens are nicely satisfied with their 2. And so they're surrounding that nitrogen are 4 pairs of electrons. Here are my 4 pairs of electrons. A very useful caret, right? It's got 4 pairs of electrons. And all I'm going to do is I'm going to say, hey, look, here's this nitrogen. It's got 4 pairs of electrons. They're going to repel each other. 4 pairs. 4 pairs. Tetrahedral. Okay.
Looks good.
And here come my 3 hydrogens. And now you might be able to say, you might have started to get to the point of saying, hey, this tetrahedral, I could put one here, and one there. and that's good. Or I could put one here, and one on what looks like the top. And it just doesn't matter, but we're gonna stick them on there. I'm gonna go there, on the top, and over here. And so there are my 3 hydrogens surround my 1 nitrogen, and my 1 lone pair of electrons that I'm holding onto it by which I'm holding onto it. So in this case, we've got the electron pairs are exactly the same. So the 4 electron pairs are tetrahedral, but the name we give to this shape is pyramidal. We got 1 central one and 1, 2, 3 down below. If I rotate just a hair more, there we go.
Yeah, the one on the middle atom, the nitrogen, is a little bit higher than the hydrogens on the bottom.
Correct. Bingo. Bingo. Yeah. So the molecule shape is pyramidal. I want to show you in Cengage various other shapes. So here is the 180 degrees, a linear molecule. Here is 120 degrees, when you've got 3 sets of electrons around the central atom. Here is the methane at 109.5 degrees, 4 tetrahedral, and then they start to get a little more complicated when we've got 5 things and 6 things all the way around the outside.
I think this is a great starting point for VSEPR. As you can see with the textbook and in Cengage, there are a lot more complicated ones. For now, there won't be any too difficult ones, but we might do a later video with more complicated shapes and electron shapes.
Okay, cool. That's a good idea.
Yep. Do you have anything else to add, Dr. Hunter?
Let's stop here for now and then see what comes next.
Sounds like a plan.
Okay, thank you.
Thank you.